Okay, let's get started. So before I get totally started, I just wanted to say that I saw that Trini made an announcement on Canvas that he's feeling a little under the weather, but he's still going to have his office hours over Zoom, and he's changed his times from 10:30, 11:30 to 10 to 11. And that change is permanent, but I don't know if he's decided on the Zoom being permanent or not. Either way, Zoom, 10 to 11, Trini's office hours today. And then next week, Ina, both your office hours are canceled. So next week, Ina's office hours are canceled. Today, Trini's are...
They might be postponed.
Okay, potentially postponed for Ina. But today, go to Trini's Zoom office hours, not in person. And I will still have my office hours at 11 in the same room. Cool, and I'll talk about some other logistics after we get through LDA. I don't know if this is going to be a very long session. Essentially, I'm going to go over a conceptual understanding of LDA, linear discriminant analysis, and then we'll implement LDA just through the math, but in programming. And then I'll go over the third homework assignment, briefly what we expect of you, what it's going to be like, and then we'll go from there. Happy Friday, everybody. So let's talk about some motivation for linear discriminant analysis. By the way, I will call it LDA most of the time. There is another algorithm called LDA, and if you Google LDA, it's actually the thing that comes up first, which is, I think, latent direct allocation. That's not the LDA we're talking about. I actually don't know what that LDA does. It's essentially just, I Google LDA, and then I see that option, and then I ignore it every time. So if anybody has used that, let me know what it's good for. But in this case, we're going to be using linear discriminant analysis, LDA. And let's talk about a very real-world situation when we're making an oddball-based BCI, right? So we have data in two different classes. We have target and non-target, and we have labels for those classes. So the labels in this case means we know which class a certain event belonged to. So if I have an ERP, I know that it's either from the target or non-target class, not just by looking at the ERP, which might be obvious, but I actually have a real-world label that tells me that was a target or that was a non-target. Whenever we're training a classifier on data that we have the labels, it's known as a supervised method. And when you don't have labels, it's called unsupervised. And there are things in between, like semi-supervised, but take a machine learning class if you want to learn about that. It's important to know that we only know what the true classes are during the calibration, or what we call the training phase. But when it comes time to actually utilize the speller and actually utilize our models, we're getting sample points that we don't know the class. I mean, obviously, if we knew which class a data point belonged to, we wouldn't even need a classifier, right? We would just already say, yep, that was a target, that was a non-target, because our system told us. So the real task is we want to create some automated method to tell us which class a new sample belongs to. You don't always have to use machine learning for this, depending on the signal. So for example, if you're using some alpha-based BCI, like trying to see is somebody in a closed eye relaxed state or not, all you need to do is a simple thresholding for that. So you can just say, okay, is my alpha activity higher than this value? And that value can be set by just eyeballing it and recording some data beforehand. So you don't necessarily need fancier approaches, but machine and statistical learning give us a way to learn these certain classifiers that are more robust or should be more robust. So let's take an example where we have this two-dimensional data. The dimensions themselves don't really matter. So in this case, we're just calling them x1 and x2. And in this case, we have very clearly separable classes. So we have the green circles and the teal triangles. And even just eyeballing it, we can sort of very easily, we could just draw an arbitrary line here. It'd be very easy for us to do. And we would say that, okay, everything on top of that line belongs to the green class, and everything below that blue, the line belongs to the blue class. There are a bunch of different ways to do this exact problem, right? This is a classic case for machine learning. This is not necessarily representative of the data you'll get, right? This is a very clear-cut scenario where we can divide the data. In reality, these data will be overlapped to some extent. They're not going to be perfectly separated, but it's nice to think about things using this ideal scenario. So one of the ways that we can do this is with LDA, and its name pretty much explains what it's doing. It's linear, which means that we're going to learn a linear decision boundary. And the decision boundary in this case, just imagine this line that's separating these two classes. That's essentially what we're trying to create. It's a discriminant analysis, which means that we're going to be trying to discriminate between our two classes via analysis. Some people also call it Fisher's discriminant analysis or Fisher's LDA, and it is related to quadratic discriminant analysis. The way that it's related, I'm going to try to be pretty math light for this lecture because I know that we have varying math backgrounds in this class. But essentially, LDA is a subset of QDA, and the thing that's different is, as we'll learn, is LDA assumes that both classes have the same covariance matrix, and QDA uses a separate covariance matrix for both classes. Both of these methods can be extended to more than two-class classification, but by default, they are two-class classifiers, and it's easiest to understand them when you're discriminating between two classes. And both LDA and QDA are also part of Bayes classifiers, so if you've ever worked with naive Bayes classifiers, they're all subsets of this. If you want to learn more about this, take ECE 209 with Vikash Gilja, where you actually go through and derive all of these functions and their decision boundaries. It's a good class. So we very often use LDA for EEG-based BCIs. It's one of the most cited algorithms right next to support vector machines. They're reliable, they're fast, and they're closed form, so we can very easily understand what's happening with LDA. We're not, and I guess the reason I bring this up as something that's important is because when we use something that's more complicated, like a deep neural network, a lot of the transformations are known to us, so we still know what every layer is doing from a conceptual standpoint in terms of how the layers are connected and what the weighting functions are. But it's not as easy to understand exactly what's happening with more complicated models. But with LDA or SVM, it's all open to us. There's nothing that's opaque. So again, we're trying to learn this decision boundary here. I've made it this pink line. Also, I've been trying to use colorblind friendly colors with this, but if anybody is colorblind, let me know if they can't see this, and I'll try to make modifications. So again, we have our class 1, which is our green circles, and our class, oh, I need to change that label. Hold on, let me do that right now. And our class 2, not class 1, which are these blue triangles. And the first thing that we can notice is that they have this scatter to them, right? We can sort of see that if we were to draw these circles around the two classes, that the data points fit around this circle. And the way to think about what these circles are representing is similar to what you'd see if you had just a one-dimensional scatter. So if you had a line and you had a bunch of points that were, really highly concentrated along the center or something, and there weren't really that many points spreading around, that would be an example of something that has pretty low variance, right? The data are varying not that much. This two-dimensional circle is also expressing the exact same thing, but in 2 dimensions. So this two-dimensional variance in this case is covariance. So we can see that it's varying both in the x1 and the x2 dimension, and this circle is capturing that covariance. Now, LDA wants to do 2 things. It wants to minimize the scatter or the covariance within a class. So we want to make sure that we're learning something that is going to minimize the within class scatter, and it wants to maximize the scatter between the classes. So we want the data points within a single class to be as close together as possible and easily enough to group together. And we want the distance between our classes to be as far apart as possible. And that should make some intuitive sense, right? Because if all of our points in one class are highly concentrated, at 100 feet away, and all of our other data points are in another class or 1,000 feet that way or whatever, it's going to be a lot easier for us to just point in a direction and be like, this data point belongs to that one or that one, just where it is spatially. And that's essentially what we're trying to do with LDA by minimizing within class scatter and maximizing between class scatter. So this would be an ideal way of creating a projection where these classes are separated. So a projection in this case, literally just imagine you have some sort of light that is at this source over here, and it is projecting all of these points down on some lower dimensional plane. So think of it sort of like a shadow. We're trying to learn a projection that optimally separates these two classes. So if we take all of our data points and we just move them onto this line over here, we're projecting all of these points onto this line. Really, it's a vector in reality. And what we can see is that if we were to use this projection, we're perfectly separating the green class from the blue class. So there are no blue samples that are on the green side, and there's no green samples that are on the blue side. And so all we would have to do is we'd have to say, okay, let's make some other vector that's perpendicular to this, which it would be this purple line. And we'd say that any sample that is, under a certain value is going to be in the blue class, and any value that's over a certain value is going to be in the green class. So this would be an example of an ideal projection. An example of a less ideal projection would be the exact opposite of that. So if we projected onto this line that perfectly separates the classes, we would see that all of the points would be completely overlaid on top of each other. So this would give us, essentially we would just be guessing whether or not a point belongs to class 1 or class 2 in an example like this. So this is the worst case scenario. If we learned this projection, then we've done something terribly. This is worse than random, right? This is like the worst possible case. So what we're trying to do is learn something like this, where we can take our data points, learn a vector that is going to optimally separate our data points and project our points onto that vector. And then our problem becomes very simple, which is just all we have to do is calculate what value we have to look for in terms of, is this data point bigger than this value? If so, this class, and otherwise this other class. So it all boils down to a thresholding problem. So we need a couple of key pieces of information. The first one is the class means, which we often represent with mu. And again, I've made a typo here. Well, not really a typo, I just forgot to change a value after copying and pasting. So we have the mean of class 0 up here, and then the mean of class 1 right here. And we can compute this through traditional means, right? You can just literally take the x and y positions of all the points and then calculate the mean normally, and that's how we have the mean. This is a very simple calculation. The other thing we need is the covariance matrices. So covariance is slightly harder to calculate, especially when we're dealing with a subset of samples. If we don't have the true distribution of data points, aka we don't have infinite data points, then all we can do is approximate the covariance. And there are various ways to approximate that. You could compute that using, there's a formula for computing covariance matrices. And for example, there's things in NumPy. You could just do np.cov, and you can calculate the covariance matrix. But that ends up, if you have different sized classes, so if you have more data points in class 0 versus class 1, for example, there's going to be different assumptions when you're calculating it like that. So we're going to use a slightly different method. But essentially, just keep in mind that the covariance matrix in this case is just the spread in all of our dimensions, which in this case is just 2 dimensions. Now, LDA, like I mentioned earlier, makes a very special assumption, which is that it assumes that the covariance matrix of class 0 and the covariance matrix of class 1 are the same. Now, this assumption is not always true, and there are a lot of data types where that's not the case. And when that's not the case, and you need to use independent matrices, covariance for class 0 and class 1 that are not the same, then what you'd be doing is quadratic discriminant analysis. And your decision boundary wouldn't be nonlinear, it'd be quadratic. But in our case, with LDA, we assume that they are exactly the same. Now, this turns out to not be a terrible assumption because EEG signals are very highly correlated both spatially and temporally. So if you look at any sample, so let's say you're sampling at 1,000 hertz or something, so one sample every millisecond, and you look at the sample at time point 1 milliseconds and the time point 2 milliseconds, there's going to be very little change between those samples. So they're going to be very highly correlated. This is also true for neighboring electrodes. So if you're recording from electrode PZ and you're looking at 1 millisecond, and then you're also looking at the 1 millisecond value for channel CPZ, which is next to PZ, you're going to have very high correlation between those two samples. So you end up having these Gaussian, blobs of data with EEG that satisfies the assumptions we need for LDA. So let's talk about estimating the covariance matrix. We first compute the scatter matrix. This formula can look scary maybe, but it's really not too bad. Here, xi is our data matrix. So in this case, it would be, we'd have 2 dimensions and we'd have n number of data points. And the n in this case is the total number of data points. It's not just saying, it's not n. It's not the number of data points in class 0 or class 1. It's just the total number of data points. So what we do is we can take any given data point from our matrix and subtract the mean of the class of the data point. So this is important. We're not subtracting from the mean of the entirety of the data. Our data are labeled, so we can calculate the means of our class 0 and our class 1, and we want to subtract the specific mean that we need during this operation. So in this case, mu c, the c is just a variable, and it'll either be 0 or 1 in this case, representing the mean of class 0 or the mean of class 1. We then multiply this with that exact same calculations transpose, and we sum all of those data points together. So the scatter matrix is just the sum of every single data point minus the mean of the class that that data point belongs to. Take that exact same value, multiply it by its transpose. That's the scatter matrix. If you've ever learned about scatter matrices or correlation matrices, this is a very standard set of operations. And then what we want to do to approximate the covariance matrix after that is we divide the number of samples from our scatter matrix. So we typically use capital sigma to represent the covariance matrix. So we just say sigma equals S divided by N. Now, whether you divide by N or N minus 1 depends on your distribution. In this case, since we're working with a multivariate Gaussian distribution, we divide by N. But I think if it's not multivariate, you just use N minus 1. Either way, what ends up happening is that the actual the vectors themselves don't end up changing. So even if you just use the scatter matrix, or you use the covariance matrix divided by N or N minus 1, the vectors themselves don't change, but the eigenvalues do, which don't worry, we're not going to get into eigenvectors and eigenvalues, but just for those that have done LDA through different means than what we're going to cover, just know that that's all that's happening, is you're scaling the eigenvector or the eigenvalue differently, but the vectors stay the same. And again, this assumes that the data are Gaussian and that both classes share the same covariance matrix, which is generally true for EEG signals. You could spend some time to think of counterexamples, but when we're dealing with example for the P3B in an oddball paradigm, this tends to be true. And this is good to visualize if you're not sure with a certain data set. And if anybody is going to end up working on a project this quarter and plans to use LDA, and you're not sure if your data are Gaussian or not, then come to my office hours and I can show you guys how to visualize that, and also to visualize the classifier's performance. Cool. So then when it comes to actually classifying the data, we first calculate the optimal projection vector. So the way that we do that is we create this vector W, which is, we take the inverse of our covariance matrix, and we multiply that with the mean of class 1 minus the mean of class 0. And remember that these are vectors because these are multidimensional things. In this case, we have axis x1 and x2. That's why they're vectors. And so our projection vector will also be a vector. And then all we have to do to project our data, anyone who remembers linear algebra, is we just take the dot product between our data matrix and our projection vector. So then once we have that projected data, so this is going to, in this case, we'd be projecting all of our two-dimensional data onto a single line. Then we need to calculate what the threshold is going to be, right? This is going to be, okay, if I set this value, anything that's smaller than it is going to be in class 0, and anything larger than it is going to be in class 1. And we can compute that with this formula. So it's just the projection vector multiplied by half of the two means added together. I'm not going to prove any of this to you. That can be an exercise for you. This is not a math class or a machine learning class. It's an applied class. So I want to explain everything and give you the formulas, but I find it personally more intuitive to just implement these things and see what's happening, which is what we're going to do next. And then once we have our C, we'll utilize our threshold essentially with this simple equation. So if something is greater than C, then it's going to be in class 1, and if it's less than C, it'll be in class 0. So let's implement that. And by the way, it's super reasonable to not understand all of this on the first pass. Don't worry, especially when you're looking at a bunch of equations stringed together. It can be kind of hard. The Wikipedia for LDA is actually quite good. There's also tons of really solid tutorials. And of course, I'll make my slides available and then ask questions on Piazza. We've answered a lot of questions about LDA over the years, so likely what you're answering or what you're asking is a very good question. I will caution that when you look at other tutorials explaining LDA via programming, that they tend to utilize different approaches than this. This is because most people learn PCA, principal component analysis, first, and then they learn LDA. But I don't find PCA very relevant for the work that we're doing here, so I didn't bring it up first. Yeah. Yeah, so that's a good question. The question was, how does LDA perform in a real online environment with like non-stationary data, which EEG is non-stationary. This is one of the reasons why we like LDA, is that it performs pretty well. So the issue of non-stationarity is always going to be present with EEG data, especially online. So what this means is that ideally we can collect our calibration data during the exact same session that we're going to be performing online classification. So typically what this means is, let's say you have a 3-hour EEG session, you'd spend the first 2 hours setting up the EEG and collecting calibration data, and then the remaining hour you would train your models on that calibration data and start making predictions online with that calibration. Now, if you were to use that same calibration data and then have a participant come back 2 weeks later and just like let's say, okay, we just want to do online spelling, we don't want to collect any more data, you're going to get worse performance with that same calibration data on session 2. What you can do to augment that is, still use some of that data, but then collect maybe half as much calibration data and then train on all of that, or take a random subset. But more realistically, you'd try to use like an equal part of take all the new data and then take equal number of samples from the old data, or maybe 25% or something, train a new classifier. That should perform better. And this is one thing that we really struggle to do in EEG. So some of you that have taken machine learning classes have probably heard about transfer learning before. In our cases for EEG, this would be something where, let's say we collect data from 100 participants completing an oddball paradigm, and we want to learn a classifier that we can then use to get 101st person in and not have to record any calibration data. We can just say, hey, we know what the P3B looks like and what it doesn't look like. We've recorded it from 100 people. There's no need to record that from you, so let's just start classifying right away. Let's start spelling right away. This turns out to be a pretty hard problem because of the issues with EEG. So it's non-stationary, everybody's signals are slightly different. But it's also a very active and exciting field of research, and it's something that students can explore for the final project, for example, looking at different transfer learning protocols and ways to improve classification across sessions or across participants. And yeah, one of the things you do when you collect a BCI study and you have multiple subjects, this is one of the first things you try. It's like, oh, how well, like if I take subject one's data and I learn a classifier, how well is that going to classify subject two or subject three or whatever? And by naively doing that, not super well. Typically what you want to do is learn some way of transforming the data from one subject into a space that's similar to another subject. And that's an exciting field of research. Yeah, good question. I went a little off topic, but I hope I answered the question. Very good one. Okay, let's start doing some implementations. So I have a little blank notebook, and I've done this before. I went for the Bob Ross method, so I sort of have a set of, I know what to expect in the end, but I want to walk through everything. So first, we're gonna import our standard stuff, right? We love NumPy, so we'll import NumPy as NP. And then we also want to visualize our data that we're going to create, and we want to visualize the projections and the classification boundary. So we will need the plot, and we will use matplotlib for that. Matplotlib, pyplot as plot. And then rather than using a bunch of functions, I'm going to use a single function from sklearn to create blobs. So sklearn, for those of you who don't know, is probably the most popular machine learning library, I'd guess, in the world. It's very heavily used. It's great. So from sklearn datasets, import, and this is a very funny function. It's just called make blobs, which is cool. It does exactly what it says it's going to do. All right, now we'll create a new cell. And what we're going to do is we're going to create two classes of data, just like in our example. So we'll, num components equal to 2. So this means that we're going to have two different classes. And then the make blobs function has a bunch of different things. I'm just going to copy and paste it in from my original code because it really doesn't make sense to go through all the parameters. But essentially, what we're setting here for n samples is the number of samples in each class. So in this case, one class is going to have 200 samples. The other one's going to have 800. This is not atypical, right? So we have 20% of our data is going to be in one class, and 80% is going to be in another class. This is very typical with an oddball design with a 20% target rate. The centers equals none is a weird parameter. If your data are the same size, then you can actually set the centers. I'm not going to worry about it. And then the cluster standard deviations are just the spread of the data. And then our random state, I'm just setting to 189 so that every time we generate these blobs, they'll be generated exactly the same. Okay, so now what we've done is we've created let's look at what we've done. So we have two variables that are important now. We have x, which is a 1,000 by 2 dimensional array. So we have 1,000 data points in total, and we have 2 dimensions. So think of these as dimension x1 and dimension x2, just like in the example. And then we also have the truth variable, which contains the labels of our data. So if it's 1, it's going to be in class 1, and if it's 0, then it's class 0. And again, we're going to see that this is going to be the same shape, except it's only going to have one dimension, right? Because all it is a label. These could very easily be, rather than being 1s and 0s, they could be, dog and cat or whatever, but dealing with Boolean values just tends to be easier. Okay? So then what we'll do, just to make life easy, is we're going to separate our classes into x0 and x1 variables. And the reason for this is that when we're iterating through our data and calculating the mean or calculating the scatter matrix, we want to know which class a point belongs to without having to look it up every time. So we're just going to separate the classes right away. So I'm going to create a variable x0, and I'm going to index x, and I'll use something called logical indexing. So I'm just going to say I want all of the values of x where the value of truth is equal to 0. So this is saying, don't give me every point in X, only give me the points in X that correspond to class 0. So I can run that, and then if I create a new cell and visualize that, I can see that that contains 200 points, and again, it's still two-dimensional. So that makes sense because we said I want my first class to have 200 points and my second class to have 800 points. So we can use very similar logic to create class 1. I don't know why I had 2 spaced there, but I'll keep it going. np.where truth equal to 1. And again, good to just verify that you're doing something correct, so we can see that that's 800. Cool. So now let's just plot our data. So there's multiple ways to do it. I am a heathen and I always use plot.plot. I'll never use scatter. And I very rarely use seaborn. So what I want to do is I want to plot the first dimension of x, x0. I want to plot the first dimension of x against the second dimension of x. So what I'm doing here is I'm saying, give me my variable x0. I want all of the rows, but only the first column. And I want to plot that against x0, all of the rows, and the second column. And then if you plot this normally, it's going to look really bad, right? It looks horrible. But we can tell matplotlib that, oh, actually, we don't care about the lines. We just want to treat these as individual data points. And we can just do that with giving it a little marker. So in this case, we can just say, oh, well, we could make this, make it triangles. We could make it smaller circles, whatever. And you can also give it a color by putting one of the color keywords ahead of it. So in this case, I'm going to make them red O's. Cool. And then I don't want that annoying message afterwards. And then I'm going to copy and paste this, and I'm going to do the exact same thing for class 1. But I don't want it to be red because then it would look confusing, so I'm going to make this one blue instead. Cool. So now we have our 2 classes. We can see that in this case, it's actually less ideal than the case I showed in the slides. We do have some overlap for the data points. So we can sort of imagine that this would be the optimal line to separate these 2 classes right here. But the data points are overlapping. Now, one thing that is, I guess, a little idealistic about this data is that typically we have less isotropic data, so we don't have equal variance along both dimensions. There's not a good way to do that within the make blobs function, unfortunately. You can just set a single standard deviation and it assumes that it's going to be isotropic, which means same variance along all axes. So what I'm going to do is, it's a little hacky, but I'm going to shear the data points, and I'm just going to shear x. And essentially I can just create an angle. So I'm going to set an angle theta equal to 45 degrees, but in radians. Oh, that's 56. That's 45. And what I'm going to do is, once I've created x, I'm going to apply a shear transformation to it. So I'm just going to copy and paste this. Google the linear algebra shearing. I think it's one of the first things you learn in linear algebra, so I don't feel bad not going over it. This is just the shear formula. I mean, it's very, yeah. Remember, shearing, scaling, stretching, rotating, these are all formulas you learn like first couple weeks in linear algebra. Oh, sorry, I didn't set it to the variable. So now we have more ellipsoid and isotropic data. And this is more typical of what you would see with real world data, with EEG data. And again, we still don't have this perfect class separation. So if we were to set, if we're going to reduce the alpha real quick, reduce the opacity, maybe set it to 0.8. We can visualize maybe that's too high even. Set it down to 0.4. So we can see that there are certain scenarios where points are perfectly overlapped. So, this right here is a purple point. It has exactly a blue and a red point directly on it. But we're still going to go forward, and hopefully we'll learn a projection that will still maximize the separation between these classes, even though it's not perfect. Yeah? Yeah, so in this case, it doesn't really matter. We're just considering them to be different dimensions. So you could actually imagine them as space, right? Like let's just pretend this is actually, x and y coordinates. Like let's say you're throwing darts or something and it's actually hitting a plane. In reality, the data you're going to be working with are going to be much higher than 2 dimensions. So dealing with 2-dimensional data is just convenient for visualization. But for this example, just pretend that it's actually like a plane that points have landed on. And let's say you're firing, like 2 different people are throwing darts or something, and you're trying to classify, you're trying to create a situation where, you're blindfolded, someone throws a dart, and you want to be able to tell with high confidence who threw that dart. So that can be a motivation for this. In reality, what we deal with EEG is very high dimensional data because we have tons of time points within a sample, and we also have multiple channels. So we end up dealing with like multiple 100-dimensional space, and that can be very hard to visualize. We'll talk about some of that in the 3rd assignment. Anyway, now that we have our blobs, we want to estimate our covariance matrices. So the first thing that we'll need to do is we'll need to compute the mean of both of these values. So I can just use numpy.mean. So I can say the mean of 0 is equal to the mean of x0. And when I compute that, and let's take a look at what it's done, it's calculated a single point, which, if we remember, x0 is a 2-dimensional data point. So I don't actually want to compute the mean of all of these values. I want the mean of x and I want the mean of y. So you can tell NumPy to do that by specifically telling it which axis you want to compute the mean over. So in this case, I'm going to say I want you to compute the mean over the rows. And now when I look at mean 0, I get 2 values. So I get the mean of column 0 and the mean of column 1. And then the shape of this is actually 1-dimensional, so it's just 2 by nothing. And for the math to work out, we need this to be a 2 by 1 vector. So I can just reshape it. And I can just reshape it with this function. So this is saying I want the new shape to be the size of the last dimension, which in this case is 2, and then I also want it to be 1. So now when I do that, I can see it's a 2 by 1. And we can just copy and paste this for class 1. Okay. And now we need to compute the scatter. So what we'll do is we'll initialize an array of zeros, which is just going to be sort of like a temp variable for now. Because remember, in the scatter formula, the first thing that we're doing is we're actually just adding a bunch of samples, right? So there's no division yet. We do division at the very end. So we just need to sum all of our calculations into a single variable s. So that's the first thing that we're going to do. And I'll create, and rather than calling it just s, I'll call it scatter. And we can initialize a 0 array using numpy.zeros. We can just give it the shape. So we want the shape to be, the covariance matrix is going to be the variance across both of our axes. So that's going to be, in this case, it's going to be a 2 by 2 thing. If you wanted to write code that's more recyclable, you would just say, I want it to be the size of our, of our dimensions, which is 2, by that same value. But you could very easily just write 2 by 2 here, and that'd be correct. This is just better practice. You don't want to just use magic numbers if you don't have to. Magic numbers are just hard set values in your code, by the way. Okay, so now we have our scatter matrix, and we can visualize that it's just a 2 by 2 matrix of zeros. And now what we're going to do is we're going to add points to that scatter matrix. So the way to think about the sum function is just as a for loop, where you're iterating from I to n, and you're just computing a sum. So let's do exactly that. So in this case, our n is going to be the number of data points, and we're going to do 2 different for loops. Rather than looping over just all of our data points, we're going to loop over x0 first, and then we're going to loop over x1 afterwards. So really, n0 is equal to the length of x0, right, which is the total number of data points. So if we plot out n0, we can see that that's 200. So we'll do for I in range n0. And if we look at the formula, we just want to take our sample and subtract it from the mean of that class. So we know that we're working with x's and x0. So we know that the very first thing we want to do for sure is maybe we'll set like this temp variable. We want to set temp equal to x0 I, right? Take the sample from x at I, just like that. And we want to subtract it from the mean of that class, which in this case is going to be mean 0. So that's exactly what this is doing, right? Take the data point from x, subtract the mean, the correct mean in this case. And then once we have that temp variable, we just have to compute the dot product between that value and its transpose. And we need to add that into scatter. So this is the dot product. So in this case, it'll be, you can do temp dot temp transpose. So the dot t is the shorthand notation for transpose, and dot is the notation for dot product. So we want to take this value, which is going to be a 2x2 value, just like our scatter, and we're going to add that to scatter. So we just do scatter plus equals that. So that's all I've done in this line is I've implemented this logic, although rather than iterating through n0 and all of x, we're just iterating through, rather than n, we're iterating through n0 and x0 rather than all of x. And that's just a convenience because it's just easier for us to separate our two variables and do two for loops than it is to look through the logic. So that's all this is doing. So if we look at what's happened there is if we look at scatter, it's going to be this huge giant number because all we're doing is taking the summation of this dot product and we're adding it together. And now we're going to make it even bigger because we're going to do exactly what we just did, but with x1. So now we're going to have n1 is equal to the length of x1, and we're going to iterate over n1, and we're going to say temp equals the index of x1 minus the first mean, and then the scatter thing we don't have to change. So now we're adding even more values, and we'll see that the values for scatter are even larger, right? So now that we have our scatter calculated, we can approximate the covariance matrix, just like in the formula, by dividing it by the total number of data points. So then we create our variable covariance, which is equal to scatter divided by big N, which in this case, we can get big N by taking the second dimension, the first dimension of X. Cool. So now we have our covariance approximation, and there it is. So this seems like an over approximation on some dimensions, but we'll see if the math works out. We'll see if in the end it ends up scaling correctly. Now what we're going to do is we're going to calculate that optimal projection vector. So that's what we have right here, which is equal to the inverse of the covariance matrix multiplied with the difference between our two means. And luckily we have a very convenient function for inverting the covariance matrix from NumPy. It's a bit of a mouthful, but it's NumPy linalg.inverse, so .inv, and we just give that our covariance matrix. So this is now the inverse of our covariance matrix. If you don't remember what the inverse of a matrix is, Google it, review your linear algebra notes. And what we want to do now is we want to take the dot product of this inverse with the difference between these two means. So we're going to take mean 1 minus mean 0. Okay? And we end up with a two-dimensional vector. And obviously we want to set that into a variable, which we'll call w. So again, this is just the formula right here. And now we need to do the projection. And again, this is just a dot product. So we take our array or our matrix X and we dot product it with our projection matrix. So what we can do is we can make a new variable called X projected and just use X dot dot W. So now we have projected all of our data onto that vector, and if we look at the size of xproj, we can see that it's the total number of samples, but it's only one-dimensional, because again, what we're doing, just like in this figure, is we're learning our vector, our projection vector, and we're projecting all of those points onto a single line. So now we're left with a one-dimensional data structure, which is essentially just points on a line. And we can actually visualize those plots. So we can do plot.plot, and we can do xproj. But if we do that, we're going to get some weird stuff because it doesn't really know what we want. It doesn't really know what we're passing it. So it thinks that what we're passing it is actually y values, but what we're doing is passing it x values. So in this case, it actually makes sense to use the scatter function. And I'm gonna copy and paste this because we're actually running out of time. I forget how slow it is to code and talk at the same time. But essentially what we're doing is we're saying, okay, make me a scatter matrix where I use my x points as my the projection, right? So this is giving us x points. And because it's one-dimensional, it doesn't actually matter what our y value is. So I'm just saying set all of the y values equal to 1. That's what the ones-like function is doing. And then I need to flatten this just because otherwise it makes a two-dimensional shape. And then what I can say is I already know which values correspond to which class because of our truth variable. So I can color the data points according to their classes by just saying the color mapping is going to be equal to the truth table. And then what I want to do is I want to make the points slightly transparent so that we can visualize the overlap between our points. So we see that, and then now we see that we have this really nice separation between our purple class and our yellow class. And you could see that if you drew a line maybe like right there, that you would separate the classes optimally. So let's draw that line. And that line is given to us by C, which the formula is right there. So it's going to be our projection vector multiplied by half of the sum of the two means. So let's calculate C. So C is equal to, in this case, we have to take the transpose so that the dimensions fit, but we still take the dot product of the transpose of the weight vector and half of mean 1 plus mean 0. Oh, what did I do there? Float object is not callable. What did I mess up there? Oh. Math. Okay. So now that we have our C, we can plot our C. There's a function called v-lines. There's multiple ways to plot a line. I'm just going to copy and paste this because we're almost out of time. You can do it, I promise. There you go. Oh, I need to define axes. All I'm copying and pasting right here is just boilerplate code for setting up a figure. Don't worry about what it does. I just need access to the axes to get the y limits. That's the only reason I had to do that. So now we've calculated our C, and this seems a little wrong, so I might have made a mistake somewhere in the code. That's what happens when I copy and paste. But I'll put the correct code on canvas. But what this should have done is it should have plotted C right here at the optimal boundary between these two classes. I'll have to go back and see where I made a mistake. But either way, I hopefully wanted to make this a little more intuitive. I know that these formulas are scary, but when you start implementing them and thinking about them in code, it doesn't end up being too bad. At least I hope so.